Hi, I'm Christian and I'm coordinating the hardware department at ParityQC. We design quantum computer chips based on the Parity QC architecture to realize scalable quantum computing. So in principle, the architecture is hardware agnostic, so it does not depend on the specific hardware characteristics. But of course, hardware platforms are very different. They have different topology, different connectivity or different native gates. And our mission in our department is that we implement the Parity architecture, taking into account all these features of the specific platforms to unleash their full potential. So in the following, we will introduce you to the different platforms we're currently focusing on: trapped ions, neutral atoms, and superconducting circuits.
Hi, my name is Federico and my work focuses on ion traps. Ion traps are a type of technology that use electromagnetic fields to confine ions in a small region of space. By adjusting these fields, you can control the ions in the chain. For example, you can move them around, or you can implement quantum gates to create entanglement. So one of the main disadvantages of ion chains is that ions are arranged in a linear chain. And this is not really good for quantum computation because it makes scalability harder. So suppose you want to increase the size of your system, then you only have one dimension to put new ions in your quantum computer. So that's why many research groups around the world are investigating this problem. At Parity QC, we are also investigating this problem. We study and design new layouts for ion traps that will allow you to implement the Parity QC architecture in a bidimensional array of ions. With Parity architecture, you can solve optimization problems with a constant depth algorithm. This means no matter how big is your problem, you will always need the same number of steps for solving it.
Hi, my name is Javad and I also work in the hardware department at Parity QC. You probably know that current quantum devices are pretty imperfect and noisy. That's why my main focus is figuring out how to tame that hardware-specific noise and even put it to work for meaningful computations. Have you heard of neutral atom qubits? They are an emerging candidate in the world of quantum hardware. Basically, using laser beam, one can catch and control the atoms, and even one can excite the atoms so that they can talk to each other and get entangled. The best part, though, is that they have the potential to scale up to a large number of qubits in small scales. At Parity QC, we are therefore really interested in this computing platform. Our team has already designed an atomic version of the Parity QC architecture specifically for solving optimization problems. The architecture is totally scalable, and we've made sure to avoid undesired effects. It's also completely problem independent and doesn't require any long-range interactions, which perfectly fits in with the available operations in neutral atom platforms. Plus, we provide instructions for engineering native parity gates up to high fidelities.
Hi, my name is Philipp. I'm a quantum hardware theorist working for Parity QC, and my aim is to bring the Parity QC architecture into reality using superconducting circuits. Superconducting circuits are a famous and popular way of building quantum computers, and they are used by industry and also academia worldwide. At Parity QC, we make use of a native multi-body couplers of nonlinear superconducting resonators in order to build an analog superconducting quantum simulator based on the Parity QC architecture. This allows to perform quantum annealing by changing the control fields of the resonators. But we are not limited to analog simulations. We are working towards the realization of a digital quantum algorithm on a transform-based hardware. With the digital parity architecture, we can run gates in parallel to perform quantum optimization with constant circuit depth. In addition, we can compile our algorithm to the native gate set of the hardware, such as an efficient compilation based on ZZ gates.
Okay, everyone, let's wrap it up. It was a really great pleasure to show you how the Parity QC architecture can lead to advantages on these different hardware platforms, and we will keep you updated on our future research. So thanks a lot for tuning in.